So why study graphs at all? Well, graphs are actually extremely useful, and they come up in a surprising number of places. The formal study of graphs kind of began with just with a rather silly problem, actually, in a town called Königsberg. I think it is now called Kaliningrad, Russia. Okay, so, and it was a problem pretty straightforward, which is that we've got this city, Königsberg. It's got these multiple, let's call them islands, right? And the idea here is that we've got these 7 bridges connecting these islands. How can I get from one bridge? And the puzzle was, can I cross each of these bridges once and only once, right? And you can try for as long as you want. It can't be done. Of course, somebody knows somebody's uncle who, did solve this problem. And it took until 1736 to solve this problem. It took Euler to come in, and he basically said, he looked at this problem, and he essentially turned it into a graph. He made it abstract, right? Took the map, made it abstract, and said, hey, let's represent each of these islands by a dot, and each of the bridges with a line here, and now I can analyze it mathematically. And this laid down the foundations of graph theory, and it showed, hey, if you can, that you can't do this. You can't go across each of these bridges once and only once. You have to have exactly 2 vertices, exactly 2 islands that have an even number of bridges. And as we can see here, this has 5 bridges. This has 3 bridges, 3 bridges, 3 bridges. All of them had an odd number of bridges connected to them. So that actually makes it kind of impossible to do. Now, of course, mind you, this actually problem was solved in World War II after 2 of the bridges, these ones here and here, were destroyed. These 2 bridges were knocked down and then rebuilt to create a superhighway. But hey, now it can be solved, right? So now this problem can be solved, right? Because notice that we have 2, 3 ways, and 3 ways. So only 2 islands have an odd number of vertices coming out of them. So this is the kind of the interesting problems you can get with graphs. Other applications, but let's go ahead and see. We can determine whether one node is connected to all the others, right? Is something inside a network or is it not? Can we pretty much use this to figure out, hey, can you take this course yet? Right? Or what is the shortest path? This is possibly the most common problem here, though, in graphs. What is the shortest path from one city to another? And shortest means whatever we want to mean. It can be like shortest distance, least expensive trip, least cost, right? What has the smallest total weight? This is also a very interesting problem. It gets into the whole, what is an easy problem, what's a hard problem in computer science, right? Because this is a fairly easy problem, finding the shortest route. But finding the biggest route, that's a monster of a problem. It's absurdly difficult. And that's really strange. That's really strange that basically biggest, smallest, the opposite. So obviously that's kind of intuitive. Oh, there should be about the same difficulty. But finding the largest path, the most expensive path, that's actually really hard and non-trivial. So we're going to go ahead and learn about how do we build these data structures.